Okay, Unit 1, Limits and Continuity. We are going to have our first day of notes. This is Lesson 1, the concept of instantaneous rate of change. So we are going to look at, can change occur at an instant? So when we start looking at that, it's like, what are the things in our life that we have had experiences with where we are looking at rates of change? And how fast we drive, how fast our savings grow over time, our growth rate every year, maybe unemployment rates you've looked at. We can look at that as a function, okay? And we're going to look at velocity first because, of course, when we're talking about a rate of change, the most common one that we study in physics is velocity. So we're going to consider an object that travels in a straight line. The average velocity over some given time interval can be defined as the ratio of the change in position, which is the displacement or net change, to the elapsed time period. So our average velocity, we're going to say, is the change in our position, which a lot of times our position function is s of t. A lot of times you'll see s of t as a position function. So change in position over change in time. If this was d of t, right? If that was our position function, it would be the change in the position d over the change in time, okay? So basically, change in position over change in time is average velocity. So now, when we think about that and we try to think about instantaneous velocity, the problem that we have is, well, if I wanted to do it instantaneously, let's say my position function was d, and I said, okay, well, if I wanted to look at my change in position, it would be my second distance minus my first, that's my change in position, over my second time minus my first. Okay, so this is like your y2 minus y1 over x2 minus x1, only we're talking about a d of t, so it'd be d2 minus d1 over t2 minus t1. So this is just like a slope formula, right? Basically, that is slope, y2 minus y1 over x2 minus x1. So this is like a slope formula, only we call it average velocity. So what about this thing called instantaneous velocity? Well, if I wanted to find what my instantaneous velocity at, let's say, 3 seconds is, and my function was d of t, and let's say that I knew at 3 seconds my distance traveled was 10 feet. If I was doing it instantaneously, there would be really no change in time, right? Because you're doing it instantaneously at 3 seconds. So you notice here that this is your problem when it's an instantaneous velocity using this ratio. We have division by 0. So our question here says, can you explain why we can't define instantaneous velocity as a ratio? The time interval is 0, and so we would have division by 0. So that's why we can't. So the time interval is 0. So that would give us division by 0, which we know in mathematics is not good, okay? Later on, we'll see how 0 divided by 0 is something that is, a different situation. But we'll talk about that coming up. How can you estimate an instantaneous velocity? So they're saying, well, if we can't do it, let's see, could we estimate it? Well, one way to estimate it is to say, well, what if I knew that at 3 seconds it was 10, but at 2 seconds it was 8? And let's just look at, the, just from 2 to 3, and that would be a good estimate. Or if you said, well, what if I looked at it at 2.9 seconds? and 3 seconds? Or what if I looked at it at 3 seconds and then 3.01 seconds? Do you see how if you decrease your time interval, then you're getting a more accurate estimate of instantaneous velocity? So that's what our answer to this is. How can we estimate it? We are going to make our time interval. So we're going to say by making our time interval very small. That's how we are going to estimate instantaneous velocity. We'll just look at it, you know, at 3 seconds and at 3.01 seconds, or at 2.9 and 3, something like that. So this big idea, average velocity over a very small time interval, is very close to instantaneous velocity. That is something that you need to really understand. That's like the biggest takeaway from lesson 1, and just how to calculate an estimate for instantaneous velocity. So today we're just going to be estimating instantaneous velocity. So example number 1, if you climb to the top of the Tower of Pisa and drop a coin to the ground, estimate the instantaneous velocity. So they're asking us to estimate the instantaneous velocity instantaneously at t equals 0.7 seconds. Use Galileo's formula S of t equals 16t squared to compute the average velocity. Galileo's formula, it is for free fall. It is the distance that an object travels when it's only being pulled down by gravity. So if I dropped a coin off the top of the Tower of Pisa, the reason it's falling is gravity, right? And so it's not like I threw it. I didn't give it an initial velocity. I just dropped it. And so this function is what we're going to use as our position function, or our distance function. So use Galileo's formula to compute the average velocity in feet per second over the time intervals listed below. So they have given us those time intervals. So what we're going to be doing, I'm first going to show how they got 22.56, and then we are going to do the rest of these calculations with our calculator. But think about this. If we're talking about S of t equals 16t squared, and on the time interval that they used is 0.7 and 0.71. So our S of 0.7 is going to be 16 times 0.7 squared, and our S of 0.71 is going to be 16 times 0.71 squared, okay? This 0.7 is like our first t, and then 0.71 is our second t. So if I was writing my S of 2 minus S of 1 over T2 minus T1, this is going to be my average velocity, my velocity average, right? And so we just said that this would be our 16 times 0.71 squared minus 16.0 times 0.7 squared over 0.71 minus 0.7. So go ahead and get your calculator out and calculate this formula. I'm going to go ahead and go over and do it in my Desmos. So let's go to Desmos, and I'm going to open up, because I know that my numerator is going to need to be all together. I need to put everything, that's 16 times 0.71 squared minus 16 times 0.7 squared, and then close that parenthesis for my numerator, divided by, and then I'll put another parenthesis, 0.71 minus 0.7, and close that parenthesis. sorry, I missed my 7 there. There we go. There's my 22.56. And so now you can see back in your notes how they got that 22.56. Now go ahead and pause the video, and I want you to do the same thing for these. Remember, this is going to be your T1 and your T2, right? So when you go to calculate, it's going to be your S of T2 minus S of T1 divided by T2 minus T1, right? So you're going to be using that formula and calculating those. So go ahead and pause your video and then come back and we'll see if we got the same values. Okay, so you should have gotten 22.48 on that one. You should have gotten 22.4016 on this one. 22.4008 on that one. And 22.400016 on the last one. So what you can see is that they gradually decreased as they were going down the amount of time so that they could get closer and closer and closer to that instantaneous velocity. So notice what happens here as you are calculating that average velocity. 22.48, 22.40, 22.40, 22.40. Wouldn't you estimate or hypothesize that it was 22.4? That instantaneous velocity at 0.7 seconds is 22.4. I think you would. So you could say the coin, and remember when we are writing on the AP exam, when they want you to write a response to something that is a word problem like this, they want you to go and look at the exact word problem. You wouldn't just say that the estimate for instantaneous velocity is 22.4 feet per second. You would want to say in terms of what the situation is in the word problem. So the coin is falling at a rate of about, because this is an estimate, 22.4 feet per second at t equals 0.7 seconds. So this would be a perfect, it says about, I have feet per second, because remember, when you are calculating this S, that would have been in feet, right? And when you're calculating that T, that would have been seconds, and you're dividing them, so you end up with feet per second. So it's going to be the Y values unit over the X values unit, okay? Whenever you're calculating that average velocity. So the study of rate of change is fundamental to the study of calculus. In our first example, we allowed the time interval to shrink to 0. So you can say that the average velocity converges to the instantaneous velocity, or that the instantaneous velocity is the limit of the average velocity. So that concept of limit is going to be coming up here. We're doing estimates now, but we're moving you towards that concept of limit. So we're going to look at a graphical representation of velocity. So if this function right here, this f function, was our position function, and we looked at it at time A and then again at time B. So this would be like our first t, this would be like our second t. You could see that this right here would be like our, our y1, and this next one would be our y2. Because this point would be like our T1, Y1 point, and this would be like our T2, Y2 point, okay? So if I wanted to calculate the average, basically what you would do is calculate the slope of this line. Because remember, average velocity is going to be that Y2 minus Y1 over T2 minus T1, okay? So we'd be thinking of the secant line. We call this line a secant line, and we would calculate the slope of that secant line. So that's what it looks like graphically. So it says average speed, which sometimes we call AROC, is defined by the total distance traveled d divided by the elapsed time period t. Graphically, the average speed is the slope of the secant line. There it is right there, what I just said. Analytically, average speed is the change in d over the change in t. Okay, so this is actually y and x. So, for this particular one, it's the change in y over the change in x, right? But we called it t, and I kept it y. So, sketch the secant line through AB, estimate the average velocity. They want you to estimate it by just imagining that this is like 1, 2, 3, 4, and this is 1, 2, 3, 4. So it looks like this a comma y of a would be the point 1 and then 1, 2, 3. So this is like the point 1, 3. Okay? And then this would be 1, 2, 3, 4, comma, 1, 2, 3, 4. So this is like the point 4, comma, 4. So if we were going to estimate that instantaneous velocity, it would be 4 minus 3 over 4 minus 1. So it looks like 1/3. That would be our estimate for our average speed. And so then if we wanted to say, well, okay, that's good for the average speed, but what if I wanted it instantaneously right here? Okay, instantaneously. So this is going to be the speed at a specific instant in time where t equals t of sub 0 is the limit of the average rates of change. So basically, you're taking it at one point and then really fast again at another point, but it's the amount of time is so small that it basically goes to 0. So this becomes a tangent line because it really, what we're doing is that the change in time is so small that it's basically 0, okay? So graphically, the instantaneous speed is the slope of the tangent line. So again, we would be looking at slope here, only this would be the slope of the tangent line. So this is a tangent line it's tangent to the function at the point where we want that instantaneous value. And analytically, we would need calculus to determine that instantaneous speed. So we're going to sketch the tangent line through C. And what we're going to do is, and I'm going to go ahead and redraw this so I can show you just trying to make sure that this line only touches at one point, so it's only touching at this point right here. And when we do that, we kind of want to see if it goes nicely through another point, okay? So yours is going to look a little bit different than mine. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6. The one that I wrote on my paper, on my copy of the notes, which I'm going to go ahead and try and reproduce, was crossing through at the point 5, 6. So I'm going to try and make my tangent pass through that also. I got a ruler and I tried to draw the tangent just like that and tried to see what it was passing through. So basically it's at this point 2, 4. That's my instantaneous. And then again, 5, 6. Okay? And so how did I do that? Well, I was just trying to reproduce what I had drawn. But if you just drew your line, you're going to look to see which one of these little dots it's closest to passing right through so that you can calculate an estimate of your instantaneous rate of change. Because really, if this is my tangent line that's only touching it at once, I just need to find 2 points on this line that I can calculate the slope. So this would be 6 minus 4 over 5 minus 2. So this is the estimate for my instantaneous rate of change at C, okay? And again, I said, oh, well, at C is 1, 2, 1, 2, 3, 4. So that's at the point 2, comma 4. So I'm estimating it for the instantaneous rate of change at 2, because my C would be 2 if my tick marks were just for one unit. So, again, you're just drawing the line and you are saying, hey, what's another dot that it goes through? And I was trying to reproduce what I had on my paper, but you might have used, another point. Let's say that when you drew your line that it went like this instead. Let's say it was a little bit steeper just because you drew it differently than me. And you chose that it went through this point right here, which would have been the point 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. So if you said, well, I've got my point 2, 4 and 4, 6, then your estimate would have been 6 minus 4 over 4 minus 2, and your estimate would have been 1, a slope of 1. And it seems like a big difference, but it's not. If I saw your work and it matched up that you drew the line tangent and you chose a point that you went through, this would be an okay estimate, okay? So don't get too worried whether it's exactly the same as mine or not, okay? Because it's an estimate. And for this particular one, we didn't give you a function. All we did was say draw the tangent and give us an estimate. And so to do that, you have to just pick a point, okay? So be okay with that because it's an estimate. All right, so let's look at our second example. Spin class, heart rate, and exercise. Have you ever taken a spin class at the gym? Then you know that after the class is over, your rapid heart rate decreases as time passes. So let h of t represent your heart rate. Write an expression for the rate of change of your heart rate over the time period from t equals 0 seconds to t equals 90 seconds after you have stopped exercising. So they didn't actually give us a specific function. They just said, hey, we're going to call it h of t. But I know that if I wanted to find my average rate of change, right, my velocity average, I'm going to be taking my h of 90 minus my h of 0 and divide by 90 minus 0, because that's what we do, right? And it doesn't matter that we don't know what h of t is. If you wanted to say, well, I don't like that 90 minus 0, then you could go like this and just say it's over 90. But other than that, there's nothing else you can do. This is your answer because you don't have an actual function. You just have the name of the function. Okay, example number 3. A hypercoaster is a special circuit roller coaster with a height measuring greater than 200 feet.